Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode, we're going to talk about James Webb Space Telescope. So let's dive right into it. Well, first we have to understand what the heck we are talking about. And thankfully, the name is quite clear. It's a space telescope. So it won't be on Earth. You won't be able to drive to it. Basically, it's in space permanently. Now, it's a next-gen space. So you have to understand this. We have been building space telescope from as early as 1980s. And we have made quite successful one. Two of them are very important for this. Hubble telescope. And Hubble telescope is quite important simply because it was an optical spectrum telescope. Simply means it sees what a human eye sees. It can also see a little bit in infrared, but you get the idea. It's like mostly if electromagnetic spectrum is a band like this, not long, an optical spectrum would be this is tuned for that optical spectrum. It can see a little bit here, a little bit there, but main is optical spectrum, and that is why the photographs coming directly out of this is so amazing, because it's literally how our eyes will see it if it can be as large as Hubble telescope and it can have long exposure. So that is why the images from this is so amazing, and it has tangibly expanded our knowledge, because this showed us that there are black holes at the center of the Milky Way. It showed us that there are dark matter. It showed us the acceleration of the expanding universe. Like it showed that, like, yeah, our math told that, but it's like, yeah, that is the speed, that is how it's matching, this is how much fudge factor you have to have. That's amazing. Then we come to basically uh, which telescope is this? Basically, Planet Hunter telescope. I forgot the name. I'm very sorry. Like randomly that happened. I forgot the name. So this telescope, a Planet Hunter telescope. Now this was specifically designed for one thing: find planets. Now the problem with that is that planets are small and they do not emit light. So it had a very simple observation. Basically, aimed at a patch of sky that was like there for 3,000 light years kind of zone. It was a telephoto lens kind of scenario, and it directly aimed observed the stars. Now it waited for dimming. Basically, star is there, planet goes in front of it, light dims. Now again, once of it could be anything. It could be anything in that 3,000 light year zone. It could be any asteroid coming crossing in 100 light years. How would you know? So what it did is just kept observing it, and observed it for years. So what will happen is, like, if it was a planet, it will do that again. If it was a planet and you are absolutely sure, it will do that for the third time. So if you can get 3 or 4 orbits, you can be damn sure it's a planet or something that is orbiting it. So that's how, utilizing this basically very long time data calculation, they figured out. So they saw as many planets as they're gonna see in the first go. It's just that over the year they started to confirm it. It's like, we saw this many things, this dips in light. After a time, yeah, we have confirmed it because this orbit checks out. Then they are like, okay, run the math, and it's like, okay, what will the third time the dipping will happen? It figured that out. So, relying on that, we now have a very long list of planet candidates, because you have to understand that, like, we knew planets should be there, but we didn't know how many, or how many can we expect in the out of in the Milky Way. This actually proved that this is like, yeah, your math was correct. This is what kind of planets we're gonna see. Then we have this test which was launched on SpaceX, and this is a next generation of this puppy. Basically, instead of telephoto, this is wide angle, so it's not gonna see as far, but it has a very wide field of view. Basically, it's seeing almost hemisphere, so it's quite amazing for what it's meant to do. And these two showed the world completely different perspectives. This showed the mechanism of universe, this showed mechanism of planets, and that will become more apparent why I'm talking about that. Well, then the question becomes, why the heck we are building this next gen thing? Doppler shift is the main reason for this. Think of it this way: universe is expanding. Hubble proved it. Now, what does that mean? That simply means if you want to see something back, as in back in time and in distance, as in 13 billion years, aka point of Big Bang, things that are emitting light from that point, those will be like blue light. Let's say the star was blue, it was emitting blue light again, white, which is color shifted to blue. It launches light, but here's the distance between those 2 points, basically from the 13.5 billion light years versus you, that has stretched now. So what does that mean? That inherently means the light spectrum has been stretched. So it goes to Doppler shift, it becomes red shifted. So blue will become redder, red will become even redder, okay, infrared, and infrared will get into radio waves. So that makes it necessary, so we have to have infrared telescope to observe some things that are in that, basically shifted that back. So that is why you will always see people talking about this can see further back in time. The reason for that is the more back you go in time, the more redder things get, and this is designed to see much more into infrared rather than optical spectrum. It's not like a Hubble telescope. It is a successor to it, but it's not like Hubble telescope. It's built for one thing. It's like, I'm gonna see in infrared as deep of an infrared as I can go. Now, the quote unquote technical word, because you have to understand optical spectrum is this narrow while infrared is huge. So to specify, since we can't see infrared, infrared is divided in three categories. This can see quote unquote two category, aka mid to long infrared. Now, why that's such a big deal? Well, in recent development of active optics, adaptive optics in ground-based optical telescope almost makes space telescope useless, because while a space telescope will be cool, it's just that the fact that you can have, like, instead of a 10-meter diameter, you're gonna have 30-meter diameter on Earth with adaptive optics. That telescope is gonna destroy a space telescope, and you're gonna have 10, 20 of those. Yeah, there is no point of doing optical astronomy in space at this point in time. However, when you're talking about infrared and when you want to confirm your Doppler shift theory, problem is our atmosphere glows, because Earth is not a 0 Kelvin planet. It has a heat to it, inherent heat coming from the sun, coming from its core. It's hot. So what does that simply mean? Because of chemical composition of our atmosphere is literally opaque to this spectrum. So you start from gamma rays, you start from X-rays and ultraviolet. Our atmosphere blocks it. Now, when I say block it, I do not mean like you fire X-ray torch from here, it will not go here. It simply means due to thick atmosphere of 100 kilometers, it will not reach us. So we cannot have basically any telescope that can see in X-rays. It will not see celestial things very clearly unless it's ludicrously bright. So it is opaque in that. But then you come to optical aspect. We can see it. Again, you are seeing me, so you can see it. Optical, transparent. Then we come to, because our atmosphere is not one gas, it's not like, okay, nitrogen, that's it. There are many gases mixed into it. It has a bit of up, down, and then you come to infrared. And it's like flat out. Nope. Infrared simply cannot go in. So infrared is the problem here. Now, when I'm talking infrared, I'm talking about mid to long infrared. The short infrared, again, that's infrared camera for you. But mid to long simply can't, because if you have a mid to long infrared camera and you have a cryogenically cooled its sensor to let's say absolute zero, it will see atmosphere glowing. All it will see is just the glow. It will not able to see through it. So that is why we have to build it in space. That's the reality of it. That is why we are not building any optical telescope in space, simply because opticals, we can beat it in ground, but we cannot do anything about the atmosphere. We cannot remove the atmosphere. So if atmosphere is completely opaque, like aka we can't see through it, we have to go above it, aka space. That is why this is being built. Now again, in radio astronomy also, we have some luck, because radio waves can penetrate through Earth's atmosphere. However, long wavelengths do not do that. So that's the reality. That is why we are building this space telescope. And Hubble Space Telescope is reaching its retiring point. Basically, at this point in time, it has served us for 30 years. Let that sink in. 30 years, this puppy has been working. And people are saying, yeah, the gyroscopes have failed, the computers have been replaced, the imaging sensors have been replaced, the lens issue that was there, lens issue, I'm saying, the mirror fault that was there, it has been corrected. So it has done its part, it has done its duty, and people at this point in time know for a fact that it is going to fall out of sky, because we do not have space shuttle at this point which can go and repair it anymore. So even if we wanted to do that, we can't do anything. So it's reaching end of life, we have to replace it. So that is why we are building James Webb. Now, how about the workings of it? Well, I would suggest go to Wikipedia, because this is ludicrously complex. When I say this is next gen, it is next gen. It is completely different ball game how they are building this. So let's start with simplifying it. What is the big deal about this? Well, it has a big mirror. That is the biggest deal out there. So if you want to understand something, if you are looking at it, be it whatever spectrum, be it a microwave, be it a radio wave, be it infrared, the bigger is better. There is no discussion here. Bigger is better. And there is some additional advantage also. So let's say Hubble mirror was like, if I'm standing here and if I extend my hand to the highest height, it will be more or less what Hubble mirror was. This is like a building. So it is ludicrously huge. Now it is so huge, they could not fit inside a rocket, so they made it into segments, and then they had a folding origami into it. Otherwise, it will simply not fit inside any known rocket as of now. So that's the primary mirror of it. Now the reason for this is, the bigger you make your mirror, the more resolution you get. Now you do not get too much resolution, but you do double it based on the diameter. However, in terms of how much light gathering capacity, aka how dim object you can see, that goes by cube. So it can see much further and it can see much clearer. So it is quite amazing. It's not like, okay, going from 1 Mbps connection to 5 Mbps connection. It's almost like going from 1 Mbps to 1 gigabyte per second. That is why this big mirror is such an important thing. And good thing about mirrors, they never expire. So this is quite amazing achievement. Now, because it has to be made for infrared, the main thing is everything has to be cooled. Now, what reflects infrared very well? Gold does. So it is gold coated. Now, on what gold is coated? It is coated on beryllium. Why? Basically, beryllium is very stable at cryogenic temperature. This is one good thing about beryllium. It's not that useful for most things. It's ludicrously expensive, but it is very stable. Basically, at 100 degree plus Celsius, I don't care. Minus 100, it simply does not care. So if you design it well for the temperature range you are putting it in, it will not change its shape and size. So basically, it's like this. Let's say 50 degrees Celsius, it will remain like this at minus 50 degrees Celsius. So that is quite amazing. That is why beryllium is used. So that's the foundation of it, because it has to go as close to absolute zero as it can go. Then how the heck it's gonna achieve that absolute zero? Because Earth is a heating element, sun, it's a nuclear reactor. So how the heck you gonna remain something that cold? Well, they're gonna put it in L2 point. Now L2 point is a unique point where it's basically everything is behind you. The Earth, the moon, the sun, all are behind you in single file. Basically, you are looking like this. Earth will be here, moon will be here, and sun will be here. And from your point of view, they will never change. Basically, you will have all of those things facing to you in one direction. Why that one direction is important? That allows them to block it with one shield. They will not have shield, okay, going shield like this. They don't have to do that. It's like one shield, that's it, done. So they are building a sun shield. Now this sun shield is the main backbone of the whole structure, because without it, infrared observation cannot be done, because you simply cannot cool the sensor. If sunlight hits it, it's gonna heat it up. Now you might be like, it's space, it's supposed to be cold. It is cold, it's just that we want it really cold. We want it like 4 or 5 Kelvin. That cannot be achieved if you have sunlight falling on you. Like, that is so low that it is Pluto is hotter. Let that sink in. So that is why it has 5 layers of heat shield. One layer is like aluminum and ceramic with some background. Then you have second layer, then you have third layer, then you have fourth layer, and you have fifth layer. So actually 2 or 3 layers would be more than enough. Fifth is just like to make sure that it does not heat up over time, because these layers are reflecting thing, but nothing reflects 100%. So over time heat will start to seep in. So 5 is like absolute certainty that over the lifespan, aka 10 year, it will not start to heat up. And now, what does it has in terms of instrument? Well, complicated sciencey words, but if I have to simplify, it has two main components. It has an imager, aka a camera, same way a Hubble had, and then it has spectrograph. Now, spectrograph is the interesting part, because I specified atmosphere have mixture of gases. Now, each mixture of gases reacts differently. So what does that mean? Let's say you saw the sun, whatever the star that may be, and you saw its light unobstructed. You know what it is. Like, okay, this is sun, this has a hydrogen in it working it, this is a spectrum. So the once the light starts to come in, and let's say this is a planet, it goes through its atmosphere, it will get changed by the atmosphere itself, because atmosphere has some things in it. It will react to it, it will change it. Now that will give it a signature into it. Now, to observe that signature, you need a spectrograph. This puppy has I think 3 spectrographs specifically built. So those spectrograph will allow you to actually fingerprint read the planet's atmosphere hundreds of light year away. So that is the amazing aspect. This is why it is such a big deal, because it is not only a basically Hubble killer, it's also a planet killer. It can also hunt a planet, and because they have micro shutter array, aka the imaging sensor can image 100 spectrograph at the same time. So if they are seeing it and they are like, okay, there are 30 planets here, all 30 planets can be observed at one go. That is amazing. So basically, given the time span, basically let's say this puppy works for 10 years. In 10 years they can do much more observation than any other system, flat out. It like but again, this is not supposed to hunt for planet. It's like once you know that the planet is there, then you aim it, and you aim it hopefully in the time where it's like at least 20-30 planets are crossing at the same time, and then you're like, okay, we're gonna spectrograph all of them. And that is why it has a micro shutter array. So these are the two big things. It has image, basically we're going to see the whole image, those will be sent to the people who are studying galaxies. Then you have spectrograph, data will be sent to planet hunters. So these are the workings of it. Then we come to the budget aspect, and I'm reasonably sure that is the sole reason why you even know about James Webb, because it's so over bloated, and the budget is like literally, this is how government talks about it. It's like it has a history of major cost overrun, and that's from a senator, and that's not wrong. So the whole target was started in 1997, and their target was in 2007 we're gonna launch it, and that time budget was like 500 million. They were so naive back then. So then they're like, okay, year by year. So let's say in year 2000, they're like, okay, let's start to build this. Let's make sure we launch it by 2009. And that time the budget was revised up to as high as $1.8 billion. So original was 500. Then they like, at that point, they still haven't awarded contract to anyone. But around in 2002, I think they started 2009 or something like that. They start like it was being delayed by this long, so they actually start to achieve 2008 primary design review. Basically, the design is locked down. This is what we're gonna build, and that time the budget has reached 5.1 billion dollar with a big B, and that time the target launch was 2014. That did not happen. Then we come to basically 2010. That time critical design review. Basically, you cannot change anything. Basically, go with it. Whatever you have made, just go with it. Don't change it, because the more you change it, the more money you waste. So that time the target date was moved to 2016. Budget 6.5. Same happened in 2013. Now the launch date is 2018, and the budget is 8.8 billion dollar. At this point, like around 2010's government tried to block it, but people are like, yeah, we have already spent so much money, might as well complete sunk cost fallacy. And then in 2018, now 2019 data is not out yet, but in 2018 the target date was launched to was pushed to 2021, March of 2021, and the budget as far now is 9.66 billion. That's almost 10 billion, and everybody is reasonably sure it will cross $10 billion mark. That's a lot of money. That's like lot of money. If your main goal, like even at the preliminary design phase where you stop changing anything, that time it was like $5.1 billion. Like you doubled it, and you started with like, government was sold on this project was like around $1.6 billion. So this is really, really bad management, and there are side effects of this kind of bad management. It's not like, oh, NASA has infinite money. NASA has no money anymore. It's like, it's not Apollo era where they had 1% or 5% of basically national budget. They have 0.9, 0.5%. So if you have a single project that is consuming this much money, all other smaller projects will be destroyed, because there are many smaller CubeSat projects, some R&D missions. All of those will be cancelled, because if you have poured this kind of money, this has to be continued, but you have to put hold on every small missions, and that's why it got the nickname the telescope that ate astronomy, simply because it was physically killing. Like, okay, we had the project of building this test kind of satellite. It was small and cheap. Yeah, we don't have the money. Why? Because this big puppy consumed all of it. So and you have to understand, astronomy is not something where you can be like, oh, this is infrared telescope, our problems are solved. You have to do astronomy in every single spectrum. That is why there are people who specialize in ultraviolet spectrography. There are people who specialize in radio telescopes. There are reasons for that. It's like, you don't just do one thing, you do all of the spectrum, and then you get the correct picture of the universe. And if you're like, all of the money is going into one spectrum, yeah, it has advantages, but it's not the whole picture. It's inherently is not the whole picture, because there is a whole electromagnetic spectrum. So that's why it got such a bad name. And at this point in time, to give you a context of that, what kind of money we are talking about, if you go to NASA and it's like, okay, NASA, tell me what kind of money you need to land a people on moon and make a permanent lunar base, that budget is $10 billion. Let that sink in. What is more important, a telescope that sees one spectrum or a whole human colony on moon? Because once you do that, you can do all these telescopes like a child's play. So that is the reason for this. That is why the budget people are like so hard about it. It's like, it's not worth, like nothing is worth $10 billion unless it's like a freaking, starting a lunar colony or building a, a space habitat where you can have 1,000+ people. It's not worth this kind of money, and especially given the fact that you started with like, oh, $500 million, oh, 1.6 billion, oh, $6 billion, $7 billion. Government literally put a cap that you cannot spend more than $8 billion. That happened $2 billion ago. So you get the idea. Like, it is ludicrously over budget, and it has physically killed projects. So it's not something that anybody is looking forward to it. So what we can expect in the future? Well, it is the most overpriced mission on NASA. And again, you may find some other mission, but the context of this is too damn high. It's like, to give you a context, like a $5 to $8 billion was wasted in Project Constellation. After Space Shuttle, Constellation was built. Constellation was ejected. The remaining parts from Constellation was made into Orion and SLS. So even such a large scope project was only, that kind of billions dollar. So people are at this point in time hoping that it really delivers, and it cannot be cancelled, because at this point in time, it's not that US only is spending on it. It's like Canadian government is also spending on it, and European agency is also spending on it. So it's like hodgepodge politics. And at this point, hopefully, as of me making this video, it's like March 2021, hopefully it will be launched, and pray to God this rocket does not blow up, because that will be $10 billion oopsie. So On top of that, you might be like, hey, but let's say if it actually gets there, let's say it actually does is what's supposed to do, wouldn't it be worth it? Short answer, no, because it will only work for 10 years, because that orbit is not stable enough. And because they are doing orbits on orbit, they're gonna consume propellant regularly, so they're gonna run out of propellant. On top of that, because of to maintain that cryogenic temperature, that heat shield keeps the temperature down. It makes sure that it does not heat up, but it does not drop to 5 Kelvin. To make sure they reach 5 Kelvin level, it has to consume liquid helium, and they're gonna run out of it. So at this point in time, inherently it has a maximum service life of 10 years. Maximum, be mindful, it cannot exceed that simply because it's gonna run out. And it was not designed with any replenishability or repairability in mind. It's basically built in 1990s. And thankfully now NASA has learned, and now they are like, okay, we're gonna build basically next generation's telescope in parts, and they're gonna have the ability to refuel, replenish with robotic arms. Like we had Canadarm for like 1993 or something like that. So again, future of this is like very big oof. So at this point in time, I'm not sure what we can expect, and not to mention the images are not gonna look gorgeous simply because they are not optical spectrum, so they will not look quote unquote real. Computer will do a very good job of converting that kind of image data into basically human colors, but infrared is this big, optical is this big, so mathematically that data must be awesome, but it will not look that great. And $10 billion moon mission, a fancy telescope. So this was my presentation on James Webb Space Telescope. I hope you liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, why? Okay, anyway, please press dislike, press it twice to show me your extra disappointment, and please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.